Welcome to this video on error correction. In data communication, errors can still occur even when error detection methods are used. Error correction not only finds these errors but also fixes them. There are two main ways to do this. The receiver asks the sender to send the data if an error is found, or the receiver corrects the error itself using special error correcting codes. These codes usually work well for single bit errors but not for first errors. One of the most common methods used for this purpose is Hamming code, which we will learn about next. The Hamming code, a famous error correcting technique developed by R.W. Hamming. The Hamming code can be applied to data units of any length and is based on the relationship between data bits and redundancy bits given by the formula 2 power r greater than or equal to m plus r plus 1, where m is the number of data bits and r is the number of redundancy bits. For example, if we have a 7-bit data unit, then we need 4 redundancy bits. Since 2 power 4 is equal to 16, greater than or equal to 7 plus 4 plus 1. These redundancy bits are placed in positions that are power of 2, that is positions 1, 2, 4, 8 and so on. This careful placement allows the receiver to detect and correct single bit errors effectively. Consider the data to be transmitted is 10110001 from the sender to the receiver. The R1 bit is determined using a parity check on all bit position whose binary representation has a 1 in the least significant position. That means we check bits 1, 3, 5, 7, 9 and 11. The R2 bit is found using a parity check on all bit position whose binary representation has a 1 in the second position from the least significant bit. This includes 2, 3, 6, 7, 10 and 11. We apply even parity, meaning the total number of ones should be even. Since the count of ones in these positions is odd, the value of R2, the parity bit is set to 1 to make the total even. Now let us calculate the R4 bit. The R4 bit is determined using a parity check on all bit position whose binary representation contains a 1 in the third position from the least significant bit. These positions are 4, 5, 6 and 7. We use by even parity, so the total number of ones must be even. Since the number of ones in these positions is odd, the value of r, the parity bit, is set to 1 to make the total even. Next, we calculate the R8 bit. The R8 bit is found using a parity check on all bit positions whose binary representation has a 1 in the fourth position from the least significant bit. These positions are 8, 9, 10 and 11. We apply even parity, which means the total number of ones should be even. Since the number of ones in these positions is already even, the value of R8, the parity bit, is set to 0. Thus, the final Hamming code or data transmitted is 1010 1001 110. Let us look at an example of Hamming code generation for the data 1001 101. First, we insert the redundancy bits R1, R2, R4 and R8 in positions that are the powers of 2. Then each parity bit is calculated based on specific bit position. R1 checks bits 1, 3, 5, 7, 9 and 11 gives 1. R2 checks bits 2, 3, 6, 7, 10 and 11 gives 0. R4 checks bits 4, 5, 6, 7 gives 0 and R8 checks bits 8, 9, 10 and 11 gives 1. After inserting these parity bits, the final Hamming code becomes 1001 1100 101. This encoded sequence allows both error detection and correction at the receiver side.